There we go. All right. So, section 3.2, I want to talk about the empirical rule. But before I talk about the empirical rule, I want to review something I mentioned last night. Significant scores or outcomes. So significant scores or outcomes. These could be significantly high or low. And there are a number of different ways to define significantly high or low scores from a data set. But what we use, at least at this stage, is what we call the range rule of thumb. And this was the last thing I believe I discussed last night. The range rule of thumb says that scores at least 2 standard deviations above or below the mean are significant. Specifically, significantly high or low. So that was our range rule of thumb. I'm going to give you a quick example. It's the one I used last night. Before I do that, I'm going to put a couple of formulas up here. These are the ones that we use from here on out, really. We use this little formula quite a bit in a couple of different contexts. For a sample, we have x bar plus or minus 2s. In terms of a number line, x bar is in the middle. You have steps up and down of 1 standard deviation for each step. This point here, that would be x bar plus 2s, x bar minus 2s. So these guys out here, these scores, these x values, including the endpoint, if you will, going back to basic algebra, those scores would be significantly high compared to other scores. These scores would be significantly low. So we have high scores over here, and we have low scores over here. And we have the same picture for population. Mu plus or minus 2 sigma. I'll remind people that when we work with populations, our parameters, means and standard deviations here, are in the Greek letters. And we have the same sort of picture. I'll even draw it again. We have mu in the middle, 1, 2 up, 1, 2 down, endpoints there, defines intervals, mu minus 2 sigma and mu plus 2 sigma. This does get used an awful lot in the real world. It's not special to this class. 2 standard deviations is a fairly common way to identify unusual outcomes. It's another way of referring to this. You'll hear me use that phrase again. All right, so this is where I was yesterday. And well, let's see. Let's see, there's some values out there, but if I take a look at pregnancy, the mean pregnancy length is about 268 days. the standard deviation is 15 days. So if I start with 268 in the middle, and I take 2 steps up, 15 and 15, that would be 298. 15 and 15 is 30. 2 steps down, that would be 238 in terms of days. These pregnancies out there, out here, does that show up okay on the screen? Kind of here, it's a little bit more visual, darker. The colors. So we're talking about pregnancy. These guys here would be way long, significantly long. These down here would be significantly short in length. There might be physical issues, any number of things might be in play on either end of those spectrums. So at the end of the day, the plus or minus 2 standard deviation looks like this: 268 plus or minus 2 times 15. So, as I say, I wanted to review this notion of significant outcomes, high or low, because I'm going to refer to that a couple of times in my discussion about the empirical, excuse me, the empirical rule. All right, so one more little bit of review, and then we'll get to the empirical rule. Normal or bell-shaped distributions. We usually use the word normal. We like bell-shaped because it's very, very, very visual. I'm grading the quiz 2, chapter 2 quizzes. I'm through, I believe, the first group, and people actually did pretty well. People usually do on this quiz. There was a question about a bell graph or bell-shaped distribution. There's your bell-shaped distribution. Your variable x, whatever you might be measuring, is along the horizontal axis, and then you've got a couple of things along the vertical axis. Right now, I'm just going to talk about counts or probability. We actually make do with either one or the other in most cases. The value right here in the middle is the mean mu. And you can see that the scores start low. We have a high point in the middle. Right, DDLE, there you go. And then they end up low again. And from left to right, it's at least approximately symmetric. The actual graph that we use is perfectly symmetric, but we'll talk about that at the appropriate time, certainly not tonight. So normal or bell-shaped distributions take that into account. So we've got this type of distribution for our empirical rule. This distribution, by the way, plays a very, very important role in what it is we do this semester regarding inferential statistics. So we're going to become very good at working with this. We're going to have to draw this little graph a bunch of times, but not in the sense of an algebra class where you graph X and Y coordinates. We need it to focus our thoughts, as you're going to see. So goodbye, Mr. Normal Curve. Now I'm ready to discuss the empirical rule. The empirical rule, the rule of empires. So the empirical rule requires a certain something. We need a normal distribution. So we start with a normal distribution. Data takes all types of different shapes. Sometimes they're normal, sometimes they're not. If the data do not have this quote unquote high, low, high symmetry kind of thing going on, if it's not normal, then this rule does not apply. It's got to be a normal distribution. And what it says is the following. It's got three parts. About 68% of data values lie within one standard deviation of the mean. That's the first statement. And I'm going to give you some pictures here, but there's three components to this and they all tie together. About 95% of data values lie within two standard deviations of the mean. You can keep going on with this particular process. We only go one more step, about 3 standard deviations. So when we take steps of 3 standard deviations, about 99.7% of data values lie within 3 standard deviations of the mean. I need to draw 2 pictures. Sorry. Yeah, 2 pictures. The first is going to be an illustration of the empirical rule. You need a normal distribution. So let me come over here. Pick up a fresh sheet of paper. These are my X values. We have, for this rule, we have count on the vertical axis. My graph goes up, my graph goes down. Mu smack dab in the middle. I'm going to go up and down 1 sigma. About 68% of the data values lie within 1 standard deviation of the mean. If I go 1 more standard deviation each way, so now it's plus or minus 2, 95% of my data values are going to fall within this range. And a third. So plus or minus 3 standard deviations gathers up 99.7% of all data values in any given normal distribution. This is a property of normal distributions, not what kind of thing is being measured. If the data being measured falls within this pattern, it follows this rule. Now, coming back to what we talked about just a little bit earlier, plus or minus 2 standard deviations, that's right here, here, out here, and out here, we are significantly high. And over here, significantly low, using that range rule of thumb. But that range rule of thumb is just that, a quote unquote, rule of thumb. A rule of thumb means that, yeah, it's a good place to start. Depending on what is being addressed or measured or what we have concerns about, sometimes we go much more than 2 standard deviations. Sometimes we go 3 or 4 or 5 or even 6 standard deviations away from an assumed mean before we can say something significant has happened. So this is really just an introduction to that empirical rule. It does guide our thinking, and it is a property of all normal distributions. So let me give you a real world example. IQ. It is normal with a mean of 100 and a standard deviation of 15. So the empirical rule will look something like this. Right here in the middle, we got 100. If I take a step of 15 up and a step of 15 down, that gets me to 115 and 85 on the low end. 65% of humanity finds their IQ in that range. Sorry, 68%. Wow, bad, Chris. Another step of 15 brings you down to 70 on the low end and 130 on the high end. 95% of every person you see on the street, of all the people you see on the street, that's better, have an IQ that falls within this range. And then finally, one last step up, one last step down. So 70, 60, 55 down here, 145 up here. 99.7% of humanity finds its IQ within that range. Yeah, someone, let's see, Benjamin noted in the chat that this idea of the normal distribution is very similar to what we saw with the frequency tables, the distribution, and it is entirely the same. It's really another aspect of that same notion. What's really interesting here is the way that this ends up working for us. It's really not in a direct fashion, but it's quite involved theoretically. But for us, it's really more about the doing than the theory. It's kind of interesting that way. So that's my discussion on the empirical rule. There's one other rule in there, and I will just mention it briefly to note that we do not cover something called Chebyshevs Rule. And by the way, if any homework questions regarding Chebyshevs Rule sneak in there, don't let it throw you. They don't appear on any quiz or exam. Chebyshevs Rule is similar to the empirical rule. but does not require a normal distribution. So in some sense, it's more useful because it doesn't have a requirement to be used with a particular type of distribution. You can use it with any distribution. And it's true. It's not a bad thing. The real problem is we really just don't use it, period. End of story. It appears here, disappears, and it never gets used again in the book at all. So I usually just mention it in this fashion and move on. But if you want, you can take a quick look at it. Don't let it throw you. It's a little odd, but we really work with the empirical rule. Let me bring that guy back here one last time just to review that empirical rule. So given a normal distribution, got to be normal. 68% lie within one standard deviation, 95% within two standard deviations, and 99.7 within three standard deviations of the mean of the distribution. And as I say, it's a very powerful distribution, and it ends up really being the key to our ability to do inferential statistics. Goodbye. All right, any questions on the empirical rule? Okay, I'm going to stop the recording.